Hi, this is Sarvajit Rana and this is my editorial video. I've chosen this problem 1981B from Codeforces round 949 division 2. So the problem states there is a sequence A0, A1, A2 of infinite length. Initially AI is equals to I for every non-negative integer I. So it is a sequence of a whole number from 0 to infinity. Okay. After every second, each element of the sequence will simultaneously change. AI will change to AI minus 1, AI or with AI or with AI plus 1 for every positive integer. AI, okay, A0 will change to A0 or with A1. It is saying that every number will take bitwise or with the two adjacent numbers, okay? And for the first number, which will be A0, it will take or with A1. That's it, okay? Turtle is asked to find the value of n after n seconds. In particular, if n equals 0, then he needs to find the initial value of n his side of. So after m seconds, you have to tell a number an, which can be any number, what it will change to. Like what will be its value after m seconds. Okay, that's the question. Okay, okay. So now you know what the question is saying. How we'll approach this problem. So you might think that there's a sequence, so there will be a pattern. I have written the sequence, so let's try to find a pattern first, if we can. So this is the sequence I've written till 26, 0 to 26. These are the binary representations, and this is the first second, this is the second second. So yes, you might feel like there's a pattern, like 0 turns to 1, 1 turns to 3, 2 turns to 3, and 3 turns to 7, 10 turns to 15. Like you might think that it is turning to 2 raised to the power something minus 1, but what about this 11 or this 19 or 23? So there's a problem with this approach. So it won't work, right? There's no pattern here. There's no like conclusive pattern to work with. So let's move on. So now let's think about bits, because we know that there's some bitwise operation going on. So what if there's a pattern with bits? How bits are changing? So let's take the example of 6. Okay, 6 is changing to 7 and 15. 6 is changing to 7, 15, and again it will change to 15. I'll show you how. Here's a 15. Here's a 15, and again you'll have a 15. The number that will replace 15 will be 31, but 31 is very far from 6 now, so it will take some time. Okay, so I can say that at least 4 seconds you'll have 15 here. Okay, so 6 is 110, it is 111, 111. So you might think that the unset bit is getting set every single time, like 0 is getting set here, then the 0 here is getting set here, but what about these? They, not happening. So there is no pattern in the bets as well. Okay, like I know I came to this conclusion very fast because I know that, but it won't work. Like if you want to try, you okay. So this won't work either. So for bit manipulation problems, when you've been given an array or some sort of range, you can try to like represent these numbers in bits. They sometimes show you some pattern, and you can use that in your solution. But here that is not the case because we have an infinite sequence. Okay. Now, what else we can do? This is the operation happening every second. So let's just talk about the operation and forget about the numbers. Okay. I'll write down just a subsequence of the sequence. Okay. Like A3, A4, A5, A6, A7, A8, A9. I'll pick A6. Okay. It changes to A5 or A6 or A7, and A7 changes to A6 or A7 or A8, and this changes to A4 or A5 or A6. In this is the first second, this is the 0 second. In the second second, we take the OR of these three numbers. Okay, it gives us A4, A5, A6, A7, and A8. So I think you can see what is happening. This was the original number. In the first second, it got expanded from both sides, and again in the next second, it got again expanded from both sides by 1 unit, of course. So now we have a pattern. Now we have found what we need to do. We basically need to find the OR of this range. I'll generalize it once, and then we'll work on how we are going to find that out. Okay. Hmm. So for an after m seconds, an will turn to an, or with an plus 1, an plus 2, so until an plus m, an minus 1, an minus 2, till an minus m. Okay. So this is what we have found. Okay, this is what we need to find out, solve basically. There's an edge case. If n is greater than equal to m, then this will become 0. Like the sequence will start from 0, 1, 2, 3, and we'll have to find the OR of all these numbers. Okay. So how we are going to do this? Now we'll write the code, but we need to think about the complexity. So for complexity, we need to first see the time constraints here. So what are the time constraints? Time limit is 1 second. Memory it doesn't matter, and the input is from 0 to 10 to the power 9. So this will create some problems. Let's see how. So 0 to 10 to the power 9, and 1 second is given. In 1 second, a computer does 10 to the power 7 to 10 to the power 8, somewhere around this range calculations. Okay. And if we start from 0 to 10 to the power 9 and go linearly, it will give you a TLE, because I've told you this. Okay. So what I'm trying to say is order of n linear order will not work, or anything higher. So we are left with three options: constant complexity, logarithmic, and there's also one pre-computation. This is not actually a better solution based on complexity. It is just a better utilization of the time constraint given. So I'll talk about pre-computation first. This is not the spelling, I know. So pre-computation. How does pre-computation work? This time, this loop, you have to run it no matter what. So this loop will take a certain time. We try to use that time to our advantage. Like for example, if you are asked to find uh, if a number is prime or not, you can't just start from 0 to that number every single time. That will give you a TLE in most cases. So what we do is pre-compute. We need to store every number, like if it is a prime or not. So like the algorithm is C for Philadelphia means we don't know, we don't need to talk about that now. But there's a pre-computation done in that. Okay. So pre-computation is basically storing some data that will be used every single test cases. Now, will that be applied here? That's the main topic here. No. Why? Because we don't need some pre-stored data. So this would work. So this is off to the discussion now. Now, what about logarithmic? Will this work? So when does logarithmic complexity happen? When you've been given a range, you divide it into certain equal parts. Like let's say half. You choose among these two halves, which half contains your desired result. Let's say this. Then we again cut this range into half, and again and again and again, till we get the required result. Okay. So basically the range changes from, if let's say the length of the range was n, then it changes to n by 2, then n by 4, then n by 8, and so on. This gives you a logarithmic complexity. Okay. Will this work again? No. Why? Because we are not trying to find something from a range. Like the answer will, in most cases, won't be in the range that we have just found. Okay. So this won't work either. So we are left with only one option, that is constant complexity. So now our problem is basically finding finding OR of a range in constant complexity. So in order to understand that, let's take an example: 32 and 36. We have to find the OR of this range. 32 is 33. Just observe the how these bits are changing. Okay, 35 is 1000 and 36 is okay. So every single time when you increase a number by one, the last unset bit, I'm talking from the left side. Okay, so the last will be here. So this unset bit gets set. Look, and for this it gets set here. Look, and got set, got set. So you can say that for a range like here 32 to 36, the first differing bit from the left side, the first differing bit from the left side, uh, this one, after the first differing bit from the left side, every bit would have been set for, you know, for any instance. For some instance, it was set. Okay, like in 33, you can see this bit was set, and this bit was set in 34. So when you take the OR of all these numbers, you'll notice that these will get set. So the answer will come out to be 10011. Okay. So what we did, the first differing bit from left side, after that bit, every bit will be set, including that bit as well. So that will give you the answer. For example, if I said 42 to 32, 42 is 1 uh, 60 68 4 okay, and 32 is 10000. So after this, all these will be set. Okay. So the answer will be 101111. Okay. So now you know what we need to do. This will give you this this will give you a constant complexity. So now we have completed the observation part and the mathematical part. What's left is implementation, which is very easy. All you need to do is just think about the, like, take care of the edge case and start a loop from the 30th bit, because as I told you, I'm talking about from the left left side. Okay, 30th bit to 0th bit. For int, you can take long, it won't matter. From 30th bit to the 0th bit, check the first bit that is differing. Okay, check the first differing bit. Yeah, differing bit. After that, set all the bits, and that will give you the answer. Okay, that's it. I guess there's not much left. I'll show you the code once. It is very easy. Okay, okay, I'll show you the code once. So this is the code, right? This is the code. I've started from the 31st bit because I've taken long, it will work, but for int, it won't work. Okay, so yes, I've only checked if the number is differing or not. If it is differing, I've stored that a bit, and then this is basically taking a or after setting the bits after that bit. Okay, this is what it is. Yeah. So yeah, that's it. There's not much left to the problem. So yeah, thank you.